Okay, some more core 3 trig. We're now going to look at reciprocal trig ratios. We're going to learn what secant, cosecant and cotangent are and how to calculate them in both degrees and radians. We're also going to look at the graphs of these three reciprocal trig ratios. And then next lesson we'll be looking at some identities involving these ratios and using them to solve equations and prove other identities. So far the three trig ratios we've used are sine, cos and tan. But we're now going to meet another three of these, which are cosec, which is 1 over sine, sec, which is 1 over cos, and cotangent or cot, which is 1 over tan. There are several ways of remembering which is which reciprocal goes with which. One way is that cot and tan are the only ones with t in them, and cosec and sec go with sine and cos respectively with the opposite first letters. The way I prefer though is to use the third letter. So cosec or cosecant in full is 1 over sine, the third letter is S. Sec or secant is 1 over cos, the third letter is C. And cotangent or cot is 1 over tan, the third letter is T. We also need to remember that because tan theta is sine theta over cos theta, then cot theta is going to be 1 over tan theta. So to sum up, these are the three reciprocal ratios, and we also need to remember that cot's cos over sine because tan is sine over cos and cot is 1 over tan. Okay, we're going to have a look now at the graphs of these reciprocal ratios. So I'm going to suggest that maybe you could have a think about this, put some appropriate values in, work them out using your calculator or use values you know, and see if you can plot the graphs of the three reciprocal ratios and have an idea what they look like. Right, well, hopefully you paused the presentation and had a go at them. We'll look at the sine graph first. Looks a bit like this. And 1 over sine is cosec. So we're going to have a think about what the cosec graph looks like. And hopefully you've already done this. Appropriate values. Well, cosec 0. So where does it go here? It would be 1 over sine 0. Well, sine 0 is 0. So we get infinity or undefined at that point. So we have an asymptote. So we can see the vertical axis here, if it's y equals the y-axis, is an asymptote. What about pi? Well, cosec pi. Well, again, 1 over 0, so an asymptote there too. And 2 pi. So we can see we've got asymptotes here at pi, 2 pi, and any multiple of pi. At pi over 2, sine theta has a value of 1, So cosec theta be 1 over 1 will also have a value of 1. If we choose sine 3 pi over 2, we can see there it's minus 1, 1 over minus 1 for sine, gives us minus 1 for cosec. So these points are shared by both graphs. You'll notice that the maximum for the sine graph becomes a minimum for the cosec graph. So we can already approximate the curve like so. We know that it goes up, tends to infinity as it approaches the y-axis. So we can see there there's quite a sharp sort of exponential growth thing going on if we approach it from pi over 2 towards 0. And we can now just use symmetry to fill the rest in. If you're not convinced, if you remain unconvinced by this, try some different points. Try points like 60 degrees, 30 degrees, or pi over 3, pi over 6, if you prefer to work in radians. And justify perhaps at least this part here, or at least the first quadrant part here. So what's the domain? Well, what x values can we have? What x values can't we have? Well, we can have more or less all the real x values, but no multiples of pi. So x can't equal n times pi. So no multiples of pi. The range, well, it includes the point 1 and the point minus 1, but nothing in between them, doesn't it? So y is less than or equal to minus 1, or greater than or equal to 1. Well, to find the graph of sec theta, we could use the same method. We also know that since y equals cos theta is a translation of y equals sine theta by minus pi over 2 or minus 90, that we can actually use that to just translate the graph of cosec along to make the graph of sec. So we can find the graph of y equals sec theta by simply translating the graph we've already found. We get a very similar graph, but this time our asymptotes are at pi over 2, 3 pi over 2, and so on. So x can be a member of the set of real numbers, but can't be 2n minus 1 pi over 2. And for the range, well, it's exactly the same, isn't it, as the one for cosec. Y is less than or equal to minus 1 and y is greater than or equal to 1. Again, we've now got a method for finding the graph of cot theta. If we use a similar approach to what we did for the first graph, y equals cosec theta. Again, have a go. Pause the presentation and have a try. Okay, hopefully you got something that looked a bit like that. The domain for this graph, again, we've got restrictions, but here again it's multiples of pi. So x can be any real number apart from a multiple of pi. And the range, well, like with the tan graph, the range is that y can be any real number. We sometimes meet these reciprocal functions in equations if we're solving equations or proving identities. So we'll have a quick look at one example on this. I would like you to have a try at this. I'd like you to ideally pause the presentation now and see if you can just do it. I'll then give you a little hint or two, and if you think that the hint's enough, pause it then, have a go. Otherwise, I'll show you how to do it in a minute. Okay, so the first hint would be, think what cosec theta is. What else could you write for cosec theta? So rewrite what cosec theta is 1 over sine theta, isn't it? So write 3 over sine theta. Okay, I'll show you the answer now. So remembering that cosec theta is 1 over sine theta, it's usually worth writing this because you often get a mark in the exam, a method mark for just doing that. This then becomes 4 sine theta equals 3 over sine theta. If we multiply by sine theta, we get that. Take the 4 over, square root, and it's the positive and negative root. And then from here on in, hopefully you should be comfortable. Use the sine graph to find all the solutions that fall between 0 and 2 pi. I'll leave you to do that. So pause the presentation again, and then I'll run through the answer. Okay, you can convert using the calculator, but setting to radians I would prefer. I use the graph to solve these sort of things. If you've learnt other methods at AS, I don't mind, and I don't mind helping you, but I think it's so important that you understand and are familiar with these trig graphs that I really think it's important to use the graphs to do this. Okay, so there we are. That's your positive root 3 over 2. You can see there's a value there. Well, if you put that into your calculator, you'll find that that's pi over 3. With sine, we get 180 minus pi over 3 as well. So in this case, it will be pi minus pi over 3, so we get 2 pi over 3. Then we look at the negative bit, at the minus root 3 over 2. The principal value we will get there, because you normally get values between minus pi over 2 and pi over 2 first, will be minus pi over 3. Now clearly that's not between 0 and 2 pi, but we can use that and use the graph symmetry to find the values that we need. Well, that value there is simply adding 2 pi. It's the equivalent value, isn't it, on the next period of the graph. So 2 pi, add 2 pi to that, you get 5 pi over 3. And then again, using symmetry, it's clear to see that that's 4 pi over 3. And there's your 4 solutions. Okay, well, if you had a reasonable amount of success with the part of this where you use the reciprocal ratio, and you can understand the rest of it, which you should know anyway really, in terms of solving and finding all the solutions within an interval, then you should be fine for the lesson. Failing that, you may need to go back over this presentation, this video, or maybe look at this topic on biomaths or in the textbook. Good luck.